when you get to this stage of a problem, the tempting thing to do is to divide this 8 and 4 and just say you're done with it, but you cannot just do that. It's both of these are divided by 4. So what we recommend, book always recommends if you're viewing the example, is don't even try to do that first. Save that. Go ahead and start with reducing the radical. Now on our last example, we were reducing radicals like this, and we did already see this exact one and learned that 64 times 2 is 128, and then the negative brings out an I. So we're bringing out a square root of 64, 8, an I out of that, and the 2 is left in. So we could rewrite this as negative 8 plus all of this reduces to 8I radical 2 over 4. And then reduce the fraction. So I recommend you do this first and then assess the reducing. If there is a common factor among your 3 parts, you got 2 parts up here and a denominator. You want to reduce all 3 parts. Both of these are divided by this. Everything is divisible by 4, so I'll divide 4 into 4, 4 into 8, and 4 into that 8. So it reduces to negative 2 plus 2I radical 2. And that's how we leave the answer on that. All right, let me give you a U try. So one similar to this. Take on string. All right, so reduce your radical first. So one way to do it is with the factor tree method. 75 breaks down into 5, 5, 5. Any set of 2 brings 1 out of that. So that would be a 5 out and a 5 in the radical. And then because the negative sign, there should be an I somewhere, either between or at the end. So this reduces to this. We got 15 minus that. Lots of 5s.
Would it be square root of 3?
Oh,
That's radical of 3.
Oh, yes, I'm so sorry. I'm so sorry. There's a 3 there. 3 times 25 is 75. Thank you. So where's my 3? 3 is what's left in here, isn't it? Yes, overlook me there. Yeah, so 3 is left over in the radical. 3 times 25 is the 75. I just had all those 5s on the mind. There is definitely a set of 5s that comes out as a 5. It's 3 that's left over. All right, so then if there's something common in these 3 places, you want to reduce by that. Don't consider what's under the radical. It's its coefficient that counts. All of this counts as one term, so any one part of it can be divided by this. Don't do what's under the radical with this. You're not supposed to do that actually. Something in a radical, something out of a radical can't be reduced anyway. So it's coefficient. So 5 into each part of that. Then what you've got left is 3 minus 1 radical 3. You can just show the 1 or not. Over 1, you don't need to show that. So this is how we should leave that answer. All right, so questions on those steps? Okay, the rest of the section is then add, subtract, multiplying, and dividing with imaginary numbers. So we're going to start with addition on example 4.
How do we type that in if we're working on homework? How would we type that in to get the correct answer?
There should be something that shows up on your toolbar, but you type in your 3, your subtract sign should be just either way, your radical, and then make sure side arrow.
So we wouldn't put the 1 in.
I don't think it'd count it wrong if you did. I think you're okay, but I wouldn't. I probably wouldn't. I don't think it would count it wrong though if you did type in the 1 there.
Well, whenever I put the I in the front of the radical, would that be considered wrong?
I would hope it would count it right, so I would expect that would also be counted right.
Okay.
Yeah. The program sometimes is finicky about things like that, and I know that can be frustrating. Hopefully, and it's not like every problem is programmed by the same person. So even if you think you got it figured out what they want, then the next problem you go to, they may not have been the same people. So the hope is that the program knows that I could be here or there, and it's okay. But if it's not, just, try to have patience with it and type it again. Should not matter though. It should not matter. All right. Example 4 is our addition. We can add I imaginaries, like if you have 3 plus 4I plus 5 plus 6I. I'm just making it my own example, actually. So go with me here. We'll try to just do one of each type of operation. If it's purely just addition and subtraction, you do it like terms. They're not really like terms. They're imaginaries, but they're like variables in that you combine them as such. So the 3 and the 5 can be combined to be 8. 4I and 6I can be combined to be 10I. So you add and subtract these imaginaries pretty much like you did variables, as if they were x's, but know in your mind they're not really x's. They have a value. I is the square root of -1, so it's not a variable, but we kind of treat it like it's 1 when we add and subtract. Now when we multiply, like on example 5, and I will do the one in the book on this. Example 5, we can multiply imaginaries and use the FOIL method, for example. We have 2 terms times 2 terms, and again, you act like it's a variable, even though in your mind you know it's not truly a variable. It has an assigned value, but you treat it as such in our operation. So we would FOIL the first times the first, the outer times outer, inner times inner, and last times last. Now notice the last times last is a negative. 3 times 4 is 12. We have an I times an I, which makes I squared. Now this hasn't come up in this lesson just yet, but we mentioned it at the start of the lesson. I squared has an assigned value of -1. So anytime you get an I squared in your problem, you are to change it out to -1 and then simplify. So negative times a negative is going to make that a positive 12. So you have to reduce it down a little bit. It basically, if you have an I squared, because it's -1, it will change the sign of that term. So you wind up with a plus 12 and a plus 6, which is 18, and an 8I minus 9I, which is -1I. And again, that 1 is optional. It should not matter if it's there or not. Now what does matter, what it will count you wrong for, is if you say -I plus 18, you'll get an X on that. I know it's not a big deal, but the I does need to be written at the end. Remember I said we'd come back to this. It says to always write complex numbers in the form A plus BI, meaning the real part in front, the imaginary part in the back. So that is a sticky rule that it will hold you to. So be sure to write it in that order, whether the one's there or not, those shouldn't matter. All right, let me have you do the FOIL method now as a you try. when you go through your FOIL steps, you should get these 4 terms. Because this one has an I squared, it becomes plus 21. Then the 10 and 21 makes for 31, minus 35 and plus 6 makes negative 29. And it should be in that order. How'd we do? Questions on the steps? Okay, the next thing in your book, the bottom of page 109, is called the property of complex conjugates. And it's in a green box, so that's where all these important rules always live. It says if you have an A plus BI times an A minus BI, and we'll FOIL that to prove it, it becomes A squared plus B squared. It gets rid of the imaginaries, basically. So multiplying by a conjugant, and let me talk to you a little bit about that. A conjugant means that you've got 2 terms, a binomial, one is plus and one is minus. They're the exact same 2 terms, but one's plus and one's minus. Well, every time you FOIL a conjugant, the first times the first, that's A squared. The outer times outer would be A times BI, ABI. The inner, that's all positive, would be plus ABI. And then the last times the last, you'd get a negative B squared, I squared. All right, because there's 2 B's and 2 I's. Well, the I squared is negative 1, so it just changes that to a plus B squared. And the middle parts are opposites, so they cancel out. So it always reduces to, this pattern will always reduce to A squared plus B squared. So we use this trick on the next thing. The last thing in this section is division. So look with me on example 6. All right, so this is division. We've added, combined our like terms, we've added and subtracted, kind of the same thing there, just combine like terms, and then we've multiplied, like the FOIL method. So the last thing to do with these imaginaries is to divide. So this is our divide example. When we are dividing complex numbers, we should always multiply the denominator by this conjugant idea. When you multiply by the conjugant, it will get rid of the imaginary stuff and will reduce it nicely. So the trick is, even though the directions say divide, in your mind, divide means multiply by a conjugant. Is really what it needs to have done. So 5 minus I needs to be multiplied by 5 plus I. By doing so, it will come out to just be perfect things, squared things, no imaginaries. Whatever you do to the bottom of a fraction, you'll have to do to the top of the fraction. So you wind up top and bottom times the conjugate of whatever you've got there. And then you've got to multiply it all out and reduce it. So this is a bunch of the FOIL method. So in the numerator, first, and so on, get it all multiplied out. Same thing on the denominator, multiply it out, and you can use the shortcut and just say it's going to be A squared plus B squared. So 25 plus I squared, or 25 minus 1, 24. If you want to FOIL it and see that so, that's fine too, but it's going to be 24 in the denominator. Oh, it's actually minus negative 1. It's actually going to be 26, sorry. So it's going to be 25 minus negative 1, which makes it plus. Let me just fix that. So it's going to be 25 minus the I squared. Because the I squared is negative 1, it actually makes 26. I went the wrong way there on you. Anyway, you can FOIL it to double check it and see that it's so. The first is obviously the 25. The outer and inner will cancel each other out. The last times last is where we get the I squared. Because this